Let's take a look at an application of calculus that involves displacement, velocity, acceleration, and jerk. Displacement, we can think of that as the position of an object on some sort of coordinate line at time t, and that typically is denoted as a function of time with s as the name of the function, so s of t. Velocity is the rate of change of position, and so we can think of the velocity function v of t as equaling the derivative s prime of t. Let me note that speed is the absolute value of velocity, meaning that velocity can be positive or negative, and it incorporates direction. Speed just represents the magnitude of velocity. Acceleration is the rate of change of velocity, and so we can think of the acceleration function a of t as equaling s double prime. It's the second derivative of the position function. The idea of jerk is a way to describe the rate of change of acceleration, and we can denote it with the function j of t, which would be the third derivative of the position function. We can think of changes in acceleration as jerk in the sense that if you speed up really quickly, that change in acceleration is going to cause a jerk sort of reaction. So think of driving down the road in your car and speeding up to pass someone or hitting the brakes to slow down very quickly. You're going to jerk forward or back. If you accelerate gradually, that's not going to happen. But if you accelerate quickly, if there's a fast change in acceleration, the jerk that you feel is what we're talking about here. And that's represented by the third derivative of the position function. So we start with a position function. We can describe the change in position using velocity. We can describe the change in velocity as acceleration, and that's the second derivative of the change in position. And we can describe the change in acceleration as the third derivative of the change in position. So let's take a look at an example. Suppose that Cupid is standing on the moon and shoots an arrow straight up, which, let me remind you, this is not a very smart thing to do, but Cupid isn't really famous for being smart. The height in feet of the arrow t seconds after it is shot into the air is given by s of t equals 200t minus 2.6t squared. This formula, this function, it comes from physics, and the 200 represents the initial velocity of the arrow. The 2.6 represents the effect of gravity. So let's think about a few questions related to this situation. First, after 3 seconds, how high would the arrow be? And so if you think about it, we have a variety of functions we could work with: displacement, velocity, acceleration, or jerk. We're given, this is a displacement function, and do we need to know anything about rates of change to answer that question? The answer, of course, is no. This is just talking about how high the arrow is. That's exactly what displacement is talking about. So this question is simply asking us to find the value of that initial function at 3. So if I plug in 3, I get 200 times 3 minus 2.6 times 3 squared. And we can use a calculator to figure out what that answer should be. And we end up with 576.6. Something I want to emphasize here are the importance of units. So this is the original function. The value 3 is representing 3 seconds. What comes out of the function, the height that we're talking about, is measured in feet. And so this is 576 feet. A second question, let's think about velocity and acceleration. For velocity, the velocity function, as we described up above, velocity is the derivative of the displacement function, the derivative of the position function. And so if I take the derivative, thinking about the power rule here, 200t is simply going to be 200, and negative 2.6t squared, well, bringing down that exponent, multiplying by 2, I end up with negative 5.2, and then the new exponent is just going to be 1, 2 minus 1. So this is my velocity function. The question is asking about the velocity after 1 minute, and since time is given in seconds, this means 60 seconds. The value of t is 60. So if I plug that into my function, if I plug that into the velocity function, again, the calculator can help us out here with the details. I get 200 minus 5.2 times 60, and we get a velocity of negative 112. So let's think about what that number means for a second. So the velocity is negative because what happens with the arrow, at first it goes up into the air, and then it comes back down. So the negative velocity means that the value that we're measuring, the displacement, the height of the value, it's getting smaller. That height is coming down. The units, and this again is a pretty important idea that I want to get across with this example, the units are going to be in feet per second. And that comes from the fact that we're talking about a derivative amount. This is ds over dt. The units for the ds part, the units for the numerator is feet, and the units for the dt part is seconds. So let's think about acceleration. The acceleration function, a of t, is the second derivative of the position function. It's the derivative of the velocity function. And so thinking about the derivative here, 200 is constant, so the derivative is just going to be 0 for that part. And the negative 5.2t, the derivative of that is just going to be negative 5.2. So the acceleration is actually constant. The acceleration at 60 seconds, because it's constant, is simply going to be negative 5.2. Thinking about the units for a moment, we're talking about the derivative of velocity. So what are the units for velocity? Well, we just said they're feet per second. And the derivative for time is still seconds. So combining those two, we end up with feet per second. Or more simply, we can say feet per second squared. Thinking about what this number means, the acceleration is talking about the change in velocity. Negative 5.2 means that we would expect this number, the negative 112 number, to be at 61 seconds. We would expect this number to be negative 5.2 units smaller than it is. The relationship here, it's feet per second squared, because in the next second we would expect the feet per second amount to change by 5.2 units. So another question, the next couple questions kind of put together a couple of these functions. So we have a displacement function that describes the height of the arrow, and from that we can find the velocity and the acceleration functions. Some of the questions that we might be interested in an applied situation might put these different pieces together. So for example, when does the arrow reach its highest point? So we'd like to know, the highest point of course relates to s of t. If you think about the s of t function, it's a parabola that opens downward, it passes through the origin, and so it looks something like that. And so we'd like to find the highest point. We'd like to find when we reach that peak. And there are a couple ways to do this. With a parabola, there are algebraic ways to think about where it's called the vertex, where that vertex is. But since we're talking about calculus, if you think about derivatives, what is the value of the derivative going to have to be? At that highest point, the velocity equals 0. We get a horizontal tangent line at that highest point. So one way to kind of think about where that vertex is, if we take the velocity function, 200 minus 5.2t, and set that equal to 0, that will tell us where this highest point is. And so we end up with 5.2t equals 200, and then dividing by 5.2 we get t equals 200 divided by 5.2. So let's see what that value is. Looks like we end up with 38.46 and some change. again, with this applied situation, let's think about the units. 38.46, it's a value for t, and the units for t is seconds. So this represents the number of seconds that the arrow is in the air, or whatever is up there on the moon, the number of seconds that it takes the arrow to reach that highest point. So that answers the first question, the when question. To think about the how high question, which function do we want to deal with? Is this displacement, velocity, or acceleration? Well, how high, just like in the first part, how high relates to the original displacement function. So the how high question is the value of that function at this time. 3,846.2, and the units, because this is the original function, the units is in simply feet. So let me put that into a sentence, since that's kind of a nice thing to do. I haven't done that for the earlier examples, but we could write conclusions like this in a sentence. The arrow, or let me say the highest point of the arrow, is 3,846 feet to the nearest foot. Another question that involves velocity and position would be, how fast is the arrow going when it hits the ground? So for this question, let's think again about our function. S of t equals 200t minus 2.6 t squared. And so what does hitting the ground mean? Well, that means that the value of the function is 0. Because this is describing the height, and so if it hits the ground, it's back at 0. And so we have a parabola, and we're not interested in this 0. Of course, 0 gives us 0. We're interested in the value of t over here that gives us that second 0 value. And so we can solve this algebraically. It's not too bad. We get 200. I can factor out a t, and I'm left with 200 minus 2.6t. And so there are two solutions to this. The principle of zero products says that either t equals 0, either this first factor is equal to 0, and that just gives us t equals 0, or 200 minus 2.6 t equals 0. And so this is the value of t. The solution to this equation is the one that will give us the place where it hits the ground. The time, I should say, the time at which it hits the ground. And so we end up with t, kind of working through the steps here, we end up with t equals 200 divided by 2.6 in a way similar to the solution up here. And so if I take 200 divided by 2.6, we get 76.9. That's the amount of time that it takes to go up and back down. And so to answer the question, the speed, how fast the arrow is going, well, that relates to velocity. If I plug this into the velocity function, thinking about that function, it's simply 200 minus 5.2 times the answer, times that 76.9 value. And if you think about it, that makes sense. Negative 200 makes sense. But the value is negative 200. That's the velocity, negative 200 feet per second. Thinking about the speed, though, how fast kind of suggests speed, and so we would probably want to consider the absolute value of that. So the speed of the arrow as it hits the ground is 200 feet per second. The velocity is negative because it also includes the direction, the downward direction of the arrow at that moment. One final question. There's a philosophical maybe answer here, but in terms of the calculus, is Cupid a jerk? Well, I would have to say no, right? Because the jerk function in this situation, it's the derivative of acceleration, but acceleration is constant, so the derivative is 0. Well, I hope you enjoyed the video. Thanks for watching.